Hey guys, this is Joe Johnson, your instructor. I'm going to go ahead and go over Chapter 6 for CTI 120. This Chapter 6 is probably one of the most difficult chapters in the course. Right? The reason being is IP addressing. With IP addressing, we're going to have to do some math. So we've got that going on. With IP addressing, this IP version 4, it's a bit convoluted because of the progression or the evolution of the IP numbering system. So we've had to put a bunch of fixes in and make changes to the original standard. So some of it might not seem to make sense. So what I'm going to do is, as I'm going through the lecture today, I'm going to go ahead and give you some historical perspective, tell you the reasoning behind the things that we do. So maybe it makes more sense in your mind, what we're doing and why we're doing it. So let's go ahead and get started. This is a long lecture because there's so much information in IP addressing. Basically because it's what we use. It's like the backbone of everything that we're doing in networking. So this presentation, this lesson has 74 slides. It'll probably take me about 2 hours to go over everything. So what I want you to do is maybe halfway through the presentation or maybe a third of the way through the presentation, take a break, pause the video, and then resume it. Your brain's not going to be able to absorb everything sitting for 2 hours. Your mind's going to wander. So what I want you to do is take breaks while you're watching this lecture. All right, let's go ahead and get started. So after you watch this lecture, do the labs, and finish this chapter successfully, you should be able to explain IP version 4 addressing. You need to tell me what CTI is, or classless interdomain routing notation. Some people call it CIDR notation. You need to be able to perform subnetting calculations. Now, I'm not going to hold you to that. That's really advanced. You definitely need to be able to do it for Net 125. And that's what this class is preparing you for, is Net 125. So maybe if you just get the idea of subnetting. I don't expect you to be able to answer all kinds of subnetting questions for this course. I do expect you to be able to configure an IP version 4 address, mainly in a Windows system. I need you to be able to describe network address translation and why we use it. We're going to describe IP version 6. We're going to go over the different types of addresses in IP version 6. We're going to explain auto configuration, which is a nice feature that IP version 4 doesn't provide. And then we're going to talk at the end about some transitioning methods. So moving from systems that use IP version 4, how do they get to IP version 6? IP version 6 is better in all ways than IP version 4. And if we can use IP version 6, we should. All right, let me give you some, before we get into this addressing, a little bit of historical background on the internet. So what we want to remember is, before the internet, we had something called, let me draw a little network here. So we've got these devices. We've got people on these devices, person A, person B, person C, and person D. In the beginning, we had something called circuit switched networks. So let's go ahead and write that. Circuit switch networks are similar to the telephone lines that you see on the street. If you talk to your parents or grandparents, the way the phones used to be set up, only one person could use it at a time. And basically that's what circuit switch networks are like. So with a circuit switch network, maybe the person at house A wants to call a person at house D. When they call that person on a telephone, the network creates a circuit. So the network will create a circuit from here to that device, here, into D. Now on a circuit switch network, that circuit's going to remain open during the entire conversation. No one else is going to be able to use any of these lines. So if A is talking to D with a telephone conversation, C and B are not going to be able to use those lines, because circuit switch networks create a circuit between the two devices and constantly use that until teardown at the end. So when you hang up the phone, it's going to tear down that circuit and those lines will become available again. So that was the old system, the circuit switch networks. Sometimes we use circuit switch networks still today. We typically use circuit switch networks if we want to guarantee a certain speed or a certain quality. So maybe when we're using voice or video, we want to use circuit switch networks. Now, so what happened was, this was back in like the 50s, when they had telephones. The military decided they wanted to come up and create a network in which we don't have the same problems. So I'm going to draw a network, and this network is going to be packet switched. And this packet switch network that they were developing was developed by DARPA, which is an agency of the military. And its goal was to create a resilient network in which circuits will not be tied up, and if I lost major portions of the network, I would still be able to do business. I would still be able to communicate. So on a packet switch networks, I might have these devices in between all of my computers, or end devices called routers. Okay. I would have connections between everything. And these things could be anything. They could be army tanks, they could be bases, right? So back then, everybody was worried about nukes, nukes taking out major portions of the communications network. So this packet switch network, what it would do was it would take your file and divide it into pieces. And I would send one piece at a time over the network. Now this piece that I send over the network doesn't create a circuit like a circuit switch network. Each time this piece of a file gets to one of these routers, the router makes a decision about which lines are saturated with traffic, which lines are faster, which lines are the best path to the other computer I'm trying to get to, or the other tank, or whatever it is. And what it'll do is it'll open up that connection between these two routers, and then it'll close it. And then it'll make a connection between these two routers, and then it'll close it. So at each stop in the journey of the packet, I'm closing the connection so that it frees up the wire for the other devices to be able to talk. In that way, I can have multiple conversations going on the same network at the same time. The other thing it did was it allowed us to have a piece of this network destroyed and still be able to communicate. So these routers could route information around disruptions in the network. So maybe these devices were more routers. If one of these lines got taken out, you could always find another way around. When we developed this system, we came up with a scheme for numbering the computers so that we know where the source and the destination was, and that is called an IP address. So they came up with this standard called IP. And what it does is it gives numbering, gives addresses to all of these different devices, much like a mailing address gives an address to your house so people can send you messages. So that's what this whole chapter is about. It's about these IP addresses, how the computers get the IP addresses, how the numbers are assigned. So that's what we're going to be covering in this chapter. So this was a little background on where IP addresses came from. They came from a project by the Defense Department to make this resilient network, this resilient packet switched network. An IP version 4 address is a 32-bit number divided into 4 8-bit values called octets. Each octet can have a value from 0 to 255. Okay, so that's kind of complicated. Let's break this down into parts. So we have an IP address. It's a 32-bit number. Remember, a bit is either a 0 or a 1, and it's how computers store numbers. So the address is going to be 4, 5, 6, 7, 8. I'm going to draw 32 of these because it's the best illustration for you. 2, 3, 4, 5, 6, 7, 8. And remember, these are either going to be zeros or ones. So I'm going to throw some ones in there just so that it looks like a number. 2, 3, 4, 5, 6, 7, 8. And then we need 8 more, right? So we have 8, 16, 24, and we said it's 32 bits. So 32 zeros or ones. That's kind of long, isn't it? And we have systems to be able to remember these addresses because your brain's not going to be able to remember these addresses. These long strings of numbers. So this is an IP address, 32-bit number. This is represented in binary. And remember, binary is how computers see the world. So this is what the computer sees when it looks at your IP address. Now, we live in a decimal world. We use base 10. We count by tens. Can you think of why we don't use binary in the real world, in our world, why we use base 10? We've been using base 10 for a long time. Why do you think we use base 10 and not base 2? Why do we use the numbers 0 through 9 and not just zeros and ones? The reason is humans have 10 fingers. So it was easy for us, even since the beginning of time, to count on our fingers. That's why we group things into tens. And if you've done any kind of recent work with your kids at school, we have 10 frames. Everything's grouped into tens. That's because everybody has 10 fingers. Computers don't have 10 fingers, so it uses a more primitive numbering system called binary. The problem with binary is our brains don't process binary. I can't look at this binary number and tell you what it is. There's just too much information on the screen. So what we're going to do is we're going to take this binary number and convert it to decimal so that my eyes can read it, so that my brain can read it. So what we're going to do is break this long number inside of the computer into bits. Right? So it's in bits. We're going to break it into bytes. Right? So remember, a byte is 8 bits. We also call a byte an octet. Oct meaning 8. Okay? So let's go ahead and put boxes around these. So these first 8 numbers are going to be an octet. These next 8 numbers are going to be an octet. The next 8 numbers are going to be an octet. And then the last 8 numbers are going to be an octet. And again, why do we break it into 8s? Because we want to convert it to a number that our brain can understand. Okay? So each octet can have a value of 0 to 255. Okay? We need to remember 0 to 255. The reason the value is between 0 and 255 is I can count up to 255 using 8 bits. So an octet can represent all the numbers from 0 to 255. That's the reason why we can't put any number higher than 255 in these octet spaces, is because we can't physically count higher than 255 with 8 bits. So what we're going to do is convert this binary into decimal numbers so my brain can understand it. So if I take a look at this, these are all zeros. So I'll put this as equivalent to 0. So this number right here in binary equals a 0 in decimal. Okay. This next number in binary is all zeros. So let's just write it as a decimal 0. This number right here is 128. I know that because I've been working with binary a lot. So it's 128 plus 16. 128 plus 16 would be 128 and 16. That would be a 4. All right, carry the 1. So maybe 144. Check my work. That's 128. That's 64. That's 32. That's 16. 7 plus 7 is 14. That's a 4. All right, I think that's correct then. So that number would be 144. This one right here, I can take a look at it and know it'll be a 6. Okay, that's the 4's place. That's the 2's place. So I know that's a 6. So this number in binary is going to equal this number in decimal, and what I'm going to do is after each octet I'm going to put a period. So the decimal equivalent of this long number is this decimal number right here, which is a lot easier for you to remember. So if I told you to remember this decimal address, you could probably tell me tomorrow. It's going to be 0.0.144.6. So we can ease, that kind of rolls off the tongue. I can tell you that really fast. Whereas if I had to tell you 0.000000000, it would take me a long time to communicate that to you. So we're going to use decimal in order to work with the numbers easier. So so that's an IP address. It's going to look like that. We also have another number called a subnet mask. A subnet mask is going to look similar. It's going to look something like 255. Remember, these numbers need to be between 0 and 255. 255.0.0. So the subnet mask is going to be similar to the IP address. It's going to have the same format. The IP address tells me which computer I want to talk to. All right. The subnet mask is also a 32-bit number, so it's going to look just like the same 32 bits. The difference is the subnet mask is going to determine what part of the IP address belongs to the network and what part of the address belongs to the computer or host. If you want to think, so the difference between a network ID and a host ID would be like when you send mail through the post office. You have a house address, 123, and then you have a street address, Main Street. So the host ID would tell you which house on the street you want to talk to. The network ID would tell you which street that house is on. So just like we send mail through the post office and we have a number to a house and then we have a street that the house is on, we have networks. So we have portions of the internet broken up into networks, which are like streets. And then on those streets we have houses. On those networks we have hosts or computers. When written in binary ones, the subnet mask that correspond the subnet mask corresponds to the bits in the IP address. So they match up. They're the same length. So here's an example of what I just did. Here's an example of, what kind of number is that? That's binary, right? We went ahead and put periods in it so it's easier to read. And this is going to be what? That's called decimal, right? It's base 10. So this is our IP address here. And this is our subnet mask. So what we just talked about on a previous slide. In order for you to use the IP address and the net mask to figure out what network you are on, you're going to have to do something called a binary AND. It's a logical operation. Let me show you the truth table. So this logical operation is kind of like addition, except it works differently. I'm going to take two numbers. Just like in addition, I take two numbers and then I get an output. I get 1 plus 1 equals 2. Our AND function is going to have the same thing. It's going to take two inputs. Okay? And this truth table here tells us that if we try to put together two zeros, we get a 0 out. If we put a 1 and a 0 into our AND formula, we get a 0. If we get a 0 and a 1, we also get a 0. The only possible way you can have a 1 from ANDing two numbers together is if the two original numbers are both 1s. Okay? Think about AND, right? When somebody offers you something, they say, do you want milk and cookies? That means both, right? There's another function called OR, where I get a 1 if either or of either of the numbers is a 1. This function is AND, so AND means both have to be true or have number 1. So that's how you AND two binary numbers. So if I feed two zeros in, it's a 0. If I feed a 1 and a 0 into the AND function, it's a 0. A 0 and a 1, doesn't matter which order the zeros and 1s come in, I get a 0 out. The only way I can have a 1 is if both inputs are 1. So look at this example here. It takes an IP address here. So this is our IP address. This is our net mask, subnet mask. So what it's going to do, the computer, and you, if you want to figure out manually which network this computer's IP address is on. Right? So we use the IP address and the subnet mask to figure out what network the computer's on. Oop. 1 second. Let me go ahead and try to fix that. right, there we go. So the reason we're doing this AND is to figure out which network this computer's on. The reason we need to figure out which network the computer's on is we need to know whether we need to send it over the internet or if I'm going to deliver it locally on the same network that I'm on right now. So the subnet mask is very important. Without using the subnet mask, if you don't add the subnet mask into the computer's not going to be able to figure out whether the computer that's trying to talk to is on the same network or not. And I believe it's required. So you have to put an IP address and a subnet mask. A default gateway is something we'll get into later. That is optional. You don't have to put a default gateway in. Right. So back to ANDing. Notice these first two numbers are a 1 and a 1. And when I AND two ones together, do you remember what I get? I get a 1. So that's this one right here. When I AND together a 0 and a 1, do you remember what I get? I get a 0. So you take each bit in the IP address and the subnet mask and you AND them together, and then you get a number out at the bottom. So for the IP address 172.31.100.6 and the net mask 255.255.00, the network that this computer is on is going to be the 172.31.0.0 network. So we took these two numbers together, we ANDed them, the binary values, and then we got this as the answer, as the output of the ANDing operation, and the output tells us what network we're on. Remember, the reason we need to know what network we're on is we need to know whether the packet that we're sending can be delivered to a computer on our network or if I have to send it to a router to go out on the internet. So that's like the first step of communication is I'm figuring out, does it need to stay here on my street or do I need to send it to another city in another state? That's why we use the IP address and the subnet mask. Computers do this automatically. They do it very quickly. If you need to do it manually, it's going to take you some time. But we need to know how to do it. We need to know how to convert from binary to decimal. And I did that very quickly in a couple slides ago. All right. So if we want to convert binary to decimal, what we need to know is we need to remember to place values of the binary system. Remember, we can have 8 bits in the number. Okay, so I'm going to draw 8 boxes. So in our numbering system, these boxes have different values. Okay? So our first, so let me write a number. I'm going to write 1, 2, 0. All right. And this is going to be decimal, so that'll put a $sign in front of it. So you can just look at this and say, oh, that's $120. It's because your brain has been taught to think in decimal. Okay? What your brain is doing is it knows the different place values of these spots. So this spot here is worth 1. The place value of this place here is 10. Okay? The place value for this slot here is 100. So in a decimal system, every place that you have a number, the value of that number is multiplied times 10. Okay, this would be the thousands place. This would be what, the 10,000s place? And what your brain did was it multiplied the number that's in the place times the value. And your brain did that automatically. So it said 1 times 100 is 100. Then it looked at the next value and it said 2 times 10 is 20. We don't have anything in the ones value, so we'll just put a 0. We add that together and we get the value 120. It's pretty simple. Your brain does it fast. Okay? Your brain does not do binary very fast. Okay? So base 10 or decimal is the places are multiplied times 10 every time you move a place over. Let me show you what binary looks like. We're going to go ahead and make a new picture. We're going to use the same places. Okay, so in binary we have 10 possible values for our numbers. Our numbers can be between 0 and 9, right? So each one of these places you can have the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9 in all of those places, and that's going to give you a value, right? Remember, in binary, we don't have 0 through 9 in binary. We have 0 or 1. There is no 2 through 9 in binaries, all zeros and ones. Okay? The place values are also different in a numbering system. So just like decimal, the value of this first slot is 1. But for the binary system, we just double the value every time we move a slot. 1. We double 1, that's 2. We double 2, that's 4. We double 2, that is, what you think it would be? 8. Okay. We double 8, what would that be? 16. We double 16, that's 32. We double 32, that is 64. We double 64, that's 128. So these are the place values we need to know in binary. There are other place values, but because the IP version 4 can only have 8 bits, you only need to know up to that place value. I'm going to go ahead and write a value, a decimal binary value, in this these boxes here, and we'll convert it very quickly. All right. So we have a binary number of 0, 0, 0, 1, 0, 1, 1, 0. In order for my brain to interpret that, I want to convert it into decimal. So what I do is I draw my boxes here. I put the numbers in these place values, in these spaces. I figure out the value of each one of these spots, these places. You should be able to convert binary and decimal after this chapter. That is something you need to pick up in this class. Subnetting, not so much, but this binary conversion you need to know how to do. So we're going to multiply that. We're going to get 0, because 0 times 1 is 0. 2 times 1 is 2. 4 times 1 is 4. 0 times 8 is 0. 1 times 16 is 16. 0 times 32 is 0. 0 times 64 is 0. Remember, anything times 0 is 0. 0 times 128 is 0. I add all these numbers together. 16 plus 4 is 20, plus 2 is 22. So the decimal equivalent of this number right here is 22. That is how you convert binary to decimal. You figure out the place values of the number, and then you just multiply the places where you have a 1 times its place value. So it's pretty easy. It's not complicated. So we need to be able to convert binary to decimal. That's one of the things we need to be able to do. Converting decimal to binary. It's a little bit different. Okay, let me clear it off and get a clean slide, and we'll do an example really quickly. Okay, so we have a number. Let's do a number 140. I want to convert 140 into binary. So I have a number that's easily recognizable by me. I want to go ahead and take that number and convert it to binary, a format the computer can see. The way you do the conversion is you just keep dividing by 2. Okay. So let me go ahead and write this differently. Let me start at the bottom of the screen because that's going to work better. All right, so we said 140. So to begin converting this to binary, we're going to divide 140 by 2. 2 into 140 is 70. What's the remainder? The remainder of the division is 0. Okay. In math, we don't call this a remainder, we call it modulus. So the modulus for 2 into 140 is 0. Okay. We're going to divide again by 2. Okay. 2 into 70 goes 35 times. Correct? 35 times 2 equals 70. What's the remainder? The remainder is 0. We're going to divide by 2 again. 2 into 35 is 14, right? Nope, 17. 17. But now we have a remainder, right? Because 2 times 17 is 34. We're going to have a remainder of 1. We're going to divide by 2 again. 2 into 17 goes 8 times. What's our remainder? Our remainder is going to be 1 since it's an odd number. So anytime you have an odd number, you're going to get a remainder of 1. 2 into 8 is 4 with a remainder of 0. 2 into 4 is 2 with a remainder of 0. 2 into 2 is 1. Okay. So let's see. Let's write what we've got so far. 0, 0, 1, 1, 0, 0. Okay. Okay. 2 into 1 is 0 with a remainder of 1. Okay. Okay. So what I've done is I've taken these remainders and I've written them down in a line. And this string of numbers here is going to be your decimal number in binary. So all we're really interested in is I need to be able to divide by 2 and find a remainder. So 2 into 140 has a remainder of 0, 2 into 70, remainder 0, 2 into 35, remainder 1, 2 into 17 has a remainder of 1, 2 into 8 is 4, remainder 0. You go all the way up to the top till you get to 1. Okay? Till you have, it doesn't go in any more times, and you're going to have a remainder of 1. And then I take from top to bottom and I just write that number down. 1, 0, 0, 0, 1, 1, 0, 0. So this number right here should equal 140. So all I need to be able to do is follow this process through, divide by 2, and just keep dividing by 2. Okay? To check our work, we would do our 8 boxes, just like we did in the last slide. We can convert it back to check our work, just to make sure everything is right. As you become more and more used to working with binary, you're not going to have to draw these boxes. You'll be able to just figure it out in your head. Just like you can do the decimal in your head now, you'll be able to do the binary in your head. Let's transfer this number to these boxes. Let's go ahead and write in our place values. 2, remember we're going to double it every time. 4, 8, 16, 32, 64, 128. We only need to be concerned about the place values that have a 1. So we have a 1 in 128 place values. So I'm going to add that. Plus, where do we have another one? In the 8th spot. And then we have another one in the 4th spot. Okay. 128 plus 8 is 136. 136 plus 4 is 140. So that matches that. So, in order to go back from decimal to binary, we just divide by 2 and find the modulus of each math problem, each division problem. These are place values. That's what it's showing you. You should go practice this a couple of times and then come back and watch it again if you have trouble. Practice it a few more times and then you'll have it. Okay. So practice is important for these binary conversions. All right. So now that we know how to take decimal and binary back and forth, now might be a good time for you to take a break. We've been in the lecture for 45 minutes now. So pause the video and maybe take a 10-minute break and come back, at the top of the hour. Okay, you should be back from your break. We're going to start going over the IP protocol and how it is set up. So the IP protocol, when it was written by DARPA, included classes in the addressing. Okay? So the standard categorizes the classes as A through E. So you have a class A, class B, class C, class D, and class E. Those classes are going to tell you which subnet mask to use. That's the reason we have classes. So a class A address is going to have a certain subnet mask. A class B is going to have a certain subnet mask. You should know we only use, according to the original standard, we only use addresses out of classes A, classes B, and classes C. Class D is for multicasting, which we don't cover in this course. And Class E is for experimental use. So we don't use addresses for computers from classes D and E. We only use addresses out of A, B, and C for devices on the network. How do we know which addresses are in which classes? That's a good question. The first thing we need to do to figure out what class our address is in is to look at the first number in the IP address. Okay. So we'll have an IP address similar to this. And that's what an IP address looks like. What we're going to do is look at this first number, what they call a first octet, to figure out which class the address belongs to. If this first number is between the value of 1 and 127, it's considered a Class A address. Is this a Class A address? It's not, because 150 does not fall between 1 and 127. So this is not a Class A address. Class B addresses, the value of the first number, the first octet, is between 128 and 191. Is this IP address a Class B address? Yes, it is, because 150 is between 128 and 191. You're going to need to remember these ranges: 1 and 127, 128 and 191. You need to remember those ranges, so you can identify the different classes of addresses. That's just something you have to memorize. If your IP address, the first number, the first octet, is between 192 and 223, it is considered a Class C address. If the value of the first octet is between 224 and 239, that is going to be a Class D address. Remember, we don't use Class D for computers. We use it for multicasting, which is something that we're going to do when we get into advanced networking. If the number falls between 240 and 255 of the IP address, the first number, it's a Class E address. So this next slide is going to summarize what we just said. So, if the value of the first number is between 0 and 127, it's Class A. Class B, is going to be between 128 and 191. And C is going to be between 192 and 223. And what's the significance of the class? The class tells us what the subnet mask should be. So with a Class A address, the subnet mask is always going to be 255.0.0.0. For a Class B address, the net mask is going to be 255.255.0.0. And for a Class C, our net mask is going to be 255.255.255.0. And what this is going to do, remember, when we put the subnet mask together with the IP address, it tells us what network we're on. So a Class A address, so if I have the IP address 60.70.80.90, you should be able to tell me which class that is. That's a Class A address because, look at the first number, it's between 0 and 127. Its net mask is 255.0.0.0, because all Class A addresses, when we're using classful IP addressing, is going to be 255.0.0.0. We're going to AND those together, and the network address for this particular IP address is going to be 60.0.0.0. Notice how fast I figured out this network address. The reason I can do it quickly is because I know anything ANDed with 0 is going to be a 0, right? The only way we get a 1 out of an AND is if they're both 1s. And if all of these octets are 0s, these have to be 0s. So for a Class A network, this first number identifies the street or the network I'm on. These numbers here identify the computers or host. That's the network address. Okay. So that is a Class A network. So you'll run into problems like, they'll ask you a question. How many hosts can a Class A network have? The way to figure that out is to figure out what number we can count up to with these bits here. Remember, each one of these octets is 8 bits. So if we can represent hosts or computers with 3 octets, that means I have 24 zeros and ones that I can use here. So in order to figure out the number of hosts I have, I'll have to say 2. That's the base number I'm using, the base system, the numbering system, to the power of how many bits I have, which is 24. Okay. What's 2 to the 24th? It is 16 million. So a Class A network can have 16 million computers on it. That's a big network. I don't think I know anybody that has 16 million computers and devices in their company. I don't even think Google has 16 million devices. They might. So the reason we use these different classes is to provide for different size networks. Okay? Remember, the more computers you have on your network, the more congested it is. Right? The slower the network goes. So the more computers you put on the same network, the slower the network's going to go. So these Class A networks would operate very slowly because I would have lots of computers on them. Now, since I didn't have 16 million computers in my company, it'd probably be a big waste to give me a Class A address because there'd be all of these unused IP addresses. So that was one of the problems we were running into with IP version 4, was I had these big networks with 16 million addresses, and I would give it to a school or a company, and then the company might use 500,000 of the addresses. And so I've got all of these extra addresses that I'm not using, right? So it was a big waste of addresses, which in the beginning, when it was only the military on this network, wasn't a big problem, right? When the military developed the internet and this IP system, they didn't anticipate there wasn't going to be everybody in the world on the network and private businesses. It was only going to be military computers. So they didn't think they would ever run out of IP addresses. Well, since the internet and the network has grown, now we have to provide for more devices. So this was the first problem they started having with IP version 4, is that we had a lot of wasted IP addresses. And these giant networks were becoming congested because they had so many computers on these big networks. Okay. So if we have 32 bits for the IP version 4 address, Let me go ahead and erase some of this math. I'll get rid of this. So we look back on it now and we're like, man, we've got a lot more computers, host, devices that need to be on the network than we can provide for, because we have all of these wasted addresses. So let's see how many IP addresses we can have on IP version 4. So we said the IP version 4 address, all of the addresses that we have in IP version 4 can be represented by 32 bits. So the number of addresses that we have for IP version 4 is going to be 4.2 billion addresses. That is the most addresses that we can have with IP version 4. Okay. So how many people are that live on planet Earth? All right. I think the last time I looked it was 6.9 or 7 billion. So we have 4.2 billion IPs. We have 7 billion people. So if we continue using the system, 2 people would have to share an IP address. Because there's just not enough addresses for everybody to use. And everybody wants to have their own cell phone, so we really can't share, right? So we're running out of addresses. That's a problem. Not only does everybody need an IP address, they probably need about 10 of them, because everybody has a car, everybody has a watch, everybody has a computer. So we have multiple devices per person. So IP version 4 stopped working probably about 20 years ago. People started realizing, hey, we don't have enough addresses for the need for everybody in the world. They said, we need to come up with a new standard. Well, the problem with coming up with a new standard is the new standard takes about 10 years to formalize. So anytime you have the technical community get together and they want to come up with a new rule or a new standard, they get together and there's an international organization, typically IEEE or ISO, and they get together and they argue about it. And they find out the best way to do stuff. And they want to find the best way before they standardize so that, when the standard comes out, it's the best way to do things. Because they have so much arguing, they have so much input, it takes about 10 years from the beginning when they start formalizing a standard till it's actually published. So we realize we're running out of IP addresses, but even if we realize it today, it would take us 10 years to come up with a new standard. So, to solve some of our problems while we were waiting for the new standard would be called the IP version 6, we needed to come up with some fixes, some ways that we can conserve IP addresses. So the first fix that they put in, now this system was very simple. You had Class A, Class B, and Class C addresses. And it was very simple to look at the first number and figure out the default net mask, figure out how many computers were on the network. It was very easy math. Because they put these fixes in to get us a little further down the road till a new standard came out, IP addressing became very complicated. So it wasn't meant to be this way from the beginning with all of this extra math you have to do. It became this because we ran out of IP addresses. Right? So know that if it doesn't make sense to you, that's probably because it's overly complicated. Okay? So let's move on to the next slide and see one of the things we did to try to fix our problem with us running out of addresses. First thing we tried was something called private IP addresses. Okay? And it's not called IP version 4.1, but that's what I call it, because we're revising the standard. So let's make a little change to it to get us a little further down the road. So what they did was they said not every computer on every network needs to participate on the internet. Some of our addresses might be printers. Some of our addresses might be internal computers that never need to get out to the internet. Well, let's go ahead and take one range from each one of the classes, and we can reuse those addresses as long as they never see each other on the internet. Okay? Remember, no two computers can have the same address. That would be like having two addresses in the United States on two different houses having the same address. You wouldn't know who to deliver it to. Right? So what we did was we said, you can use these three ranges, these three special ranges that we're specifying in the standard, as long as that computer never sees another computer with that address ever. So these are called private addresses. Any IP address that starts with the number 10, X. So any IP address you see with a 10 in front of it is called a private IP address. Okay. So private. Okay. That address, if a packet gets to a router with that address, the router is going to drop it. Because remember, those addresses are never meant to be put out onto the internet. It is only internally inside of your company or your network. They also specified a Class B range. So any IP address that starts at 172.16 and all the numbers between 16 and 31 is going to be a private address also. So if I see an IP address 172.30. anything after it, the router's going to drop it. These are private addresses, and the reason we do it is to conserve IP addresses. We also have another range, 192.168.0. So anything that starts with 192.168 is also going to be a private address. Remember, those addresses, any address that a router sees, cannot be routed across the internet. It's going to be thrown away. So they came up with those three ranges. There's also a fourth range. According to another standard, it's called zero config. So any IP address that falls between 169.254.1 and 169.254.254.255, any IP address in that range is also going to be dropped at your router. That's another private range. This range is called automatic private IP addressing, or APIPA, and it is for computers to automatically configure themselves. So there are four ranges that we need to be aware of. We've got the 10 network, we've got the 172.16 through 172.31, and then anything that starts with 192.168, and then this last one, 169.254. If your computer picks one of those addresses, or you assign that address to one of your computers, you're going to be able to print to your printer at your house. You're going to be able to get to all your devices within your network, but you're not going to be able to communicate on the internet. And again, that's for conservation of IP addresses. So they started doing that, and then more and more people found out about the internet. And they're like, I know you say I don't need the internet on this computer, but it would be nice to have the internet. So there's all of this pressure from people that want to not just have an address that can communicate inside of the company, but be able to get out to the internet. So they needed to come up with another fix because there was more and more demand for all of the computers on the network to be able to get to the internet. So they came up with another fix, another band-aid called classless interdomain routing. I call this IP version 4.2. Remember, that's not an official name of it. I just name it that because it helps me fit it in my head that, hey, here's another revision that they made to make the IP addressing work for a little bit longer. Okay. In the beginning, IP version 4, we had classful addressing, where we had the different classes. We had A, B, and C. Remember, because of the classes, we wasted a lot of addresses. Remember, a Class A address would allow you to have 16 million computers on your network. Well, that was very wasteful. So they said, we need to do away with this Class A, Class B, and Class C and be able to change the network mask. And this is where this classless addressing or CIDR notation came in. It's a type of address configuration where subnet mask could be configured regardless of the address class. So we're throwing away the classes A, B, and C. And what we're doing is we're breaking bigger networks into smaller networks. Let me show you a quick example. So I have an IP address that I'm given from my ISP. So I go to AT&T and I say I have a large network and I want to be able to resell my IP addresses to people further down. So AT&T might sell it to another company like Suddenlink. So Suddenlink's on the back of AT&T. So Suddenlink would get a Class A address of 50.60.70 network. Actually, since it's a classful address, let me go back a second. And it wouldn't be that. Let me write it a different way. It'll make more sense to you. So AT&T would give Suddenlink, one ISP would give another ISP the 50 network. Because remember, a Class A network, the first number is the network ID, the rest are host. So if you give in a Class A range, you have 16 million addresses you can use. So what this CIDR notation or classless notation allows us to do is it allows us to take this big network that has 16 million computers and break it into smaller networks. So with classful addressing, the IP address, the net mask for this network would be 255.0.0.0. And that's where we get our 16 million computers from. But what we can do now with CIDR notation, CIDR, and that's classless, is I can change the net mask. So the network I have would be, the first 8 bits would be a network ID. So I'm going to put the letter N. 2, 4, 5, 6, 7, 8. Dot. And then the bits, all the rest of the bits would be host addresses. H, H, H. So I gotta draw 24 H's. Give me a second. I'm gonna try to do it nice and neat so you'll be able to tell what I'm doing. It just takes a little while. H, 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 H. I need one more H. So I'm drawing letters, but these are actually bits, right? Zeros or ones. They just represent the host portion of the IP address. That's 24 bits, and remember the IP address is 32 bits. Let's keep going. 8 more. Five, 6, 7. There we go. So, for classful routing, for classful IP address, for the 50 network, the first 8 bits are for the network address. That's my ends. So ends equals networks. And then all the rest of these bits, the 24 extra bits, 2 to the 24th, are for computers, which we said was 16 million, right? 2 to the 24th is 16 million. We said, man, I don't need a network with that many computers on it. It would be nice to be able to break down my big network into a smaller network and then give it out to other companies, right? So AT&T might have this 50 network, and it wants it to give it out to smaller companies. So what it'll do is use this classless numbering system. They'd be given this 50 network, maybe from IANA or one of these organizations that divvies out IP addresses. Be given this big network, and what they'll do is they'll modify the subnet mask. So instead of using 255.0.0.0.0 like classful, they'll take the Class A address and then change the net mask to this. So they'll add an extra 255 in their net mask. And what that'll do is it'll take this long number and it'll make two octets or 2 sections of the IP address part of the network number. So this is a Class A address. I'm going to take the next 8 bits and I'm going to turn them into subnet bits. So I'll mark that with S. We need to separate or keep track of what bits are subnet bits, what bits are network bits, and what bits are host bits, so we can do our math. And then the rest are going to be H's again. 1, 2. Boy, I'm going to get carpal tunnel from doing this. 3, 4, 5, 6, 7, 8, and then 8 more. So our original network, our original IP address and net mask is being transformed by an ISP that's lower than the company that gave it to it. And it's taking this octet here and making more networks with it. So if we look at this subnetted network, we'll have host bits. We'll have 2 to the 16th host bits. All right. 2 to the 16th is, I think, 64,000, if I remember right. So for this particular these networks that I give out, they can have 64,000 computers on them instead of 16 million. So these networks are going to be smaller, but I'm going to have more of them because I'm taking some of these and breaking it into smaller networks. So I'm taking a Class A network, and I can have 64,000 computers on each network now, but I can divvy this bigger network into 2 to the 8th networks because those are subnet bits. So I can divide this up between 256 customers. And each of those customers are going to have 64,000 addresses on each one of their networks. So that's what CIDR notation does. It allows us to use alternative net mask in order to break bigger networks into smaller networks so that there's more IP addresses to go around to everyone. So that's why they made that modification to IP version 4. So now we don't have as many wasted addresses as we did with the classful addressing. We take a bigger network and break it into smaller networks. Since we have more networks, we can give it out to more companies and more organizations, and that in turn reduced waste. All right, let's see. When we use CIDR notation, we use a slash notation instead of writing out the net mask like we did with classful addressing. Just remember this number is going to be how many bits represent the network. So we would put the IP address that we have, and instead of writing 255.255.255.0 for this net mask, we would count how many of these bits are network bits. We figure that out, and we figure out that 24 bits are used to represent the network in this IP address, and then we just write 24 there. So the number after the slash is always going to be how many network or subnet bits you have. Having 24 network bits tells me I've got 24 from 32. I have 8 bits left over for computers. Each network is a broadcast domain. Okay. Remember, broadcast domains are the computers that are going to get a message if I send it to a broadcast address. So I have special addresses for every network that I can use if I want to send a message out to every computer. That special address is called a broadcast address. And every computer that is part of the same broadcast domain receives that message when I send messages to that broadcast address. Okay. It's a packet addressed to all computers on the network. So when you send out a broadcast, it ties up all wires on the network. As long as all of the wires are part of the same network, they're all used when I send out a broadcast. So broadcasts are very wasteful, and like I said, it turns your network into basically a circuit switch network where everything's used up all at once. Okay? All the lines are used up with a broadcast. IP version 4 relies heavily on broadcast. So some of the protocols we have, DHCP, which we use to assign addresses to computers, and ARP, which we use to translate IP addresses into MAC addresses, use broadcast. So broadcasts happen all the time on the network. Just remember that broadcasts slow your network down because it ties up all of the lines. So we've become to feel now in modern days that broadcast are really bad. When we switched to version 6, we got rid of broadcast. Okay? So you can tell that that's probably something bad if we got rid of it in a newer version of the protocol. Okay? All right. So these broadcasts go out, and it is another reason why we break our network into our network into smaller networks. When I break a bigger network into a smaller network, the broadcast domain gets smaller. Okay? Imagine if you can send a broadcast message to every computer on the internet. Okay? We can't do that because all of the computers on the internet are broken into different networks. If we didn't have those smaller networks broken down, the broadcast messages would tie up all the circuits on the internet. So that's why we need to know what broadcast is. Broadcast is going to be sent to every computer that is on the side of a router, or the computers that are on the same network. It's pretty wasteful. Okay. This is what we're talking about, CIDR notation. Subnetting is a process that reallocates bits from the host portion to the network portion, creating smaller address spaces or smaller networks. The reason we use CIDR notation or CIDR notation in subnetting is to divide very large network into smaller ones. Also to cut down on the waste, to conserve IP addresses, and to make them more secure and put them into logical groups. So there's a few reasons why we break bigger networks into smaller networks. The key reasons being we're wasting IP addresses and because of these broadcast messages. So to calculate a subnet mask, we need to figure out how many networks we need to borrow from the host portion of the addresses. Remember, when we subnet, we take some of the host addresses and we change them into subnet addresses, and then we can make more networks, which makes the network smaller, which makes our networks run faster. All right, so let's see. This is an example of a larger network being broken up into smaller ones. If all of these computers were on the same network, the network would be slower. But what we've done is we've taken a larger network and broken it into smaller networks. So now when this computer here sends out a broadcast address, only these computers within this circle receive the broadcast address. These other computers don't process those packets. All right. So let's quickly do a subnetting problem. Remember, I don't expect you to be an expert on subnetting at the end of this class, but we need to introduce it. So I contact Suddenlink, and Suddenlink gives my business a network. Let me go ahead and switch over to black. Pen. So I am given by Suddenlink an address of 119 dot 20 dot 10 dot 0, and they tell me it's a /24. Let me go ahead and convert some of these numbers. Let me use some easier numbers so that maybe they'll start clicking. Let me use numbers that are easier for you to process with your brain. So let's do 192, 128, and 64. So we're given that network from Suddenlink. And Suddenlink says you've paid your subscription, your monthly subscription, so you have this network range that you can use for any of your computers. And the 0 here means X. So I can use all of the network addresses, the host addresses for this octet here. Right? So we can write the address. The address is going to be in binary. 128 plus 64 is 192. We'll draw 6 more zeros. So we're going to have to convert this to binary to do our subnetting. All right. 128 is just a 1. 4 more zeros. Dot 64. 1, 2, 3, 4, 5, 6, and the rest are zeros. 2, 3, 5, 6, 7, 8. So let's identify these bits. We don't have a subnet mask to help us to identify which bits are subnet masks, which bits are network bits, and which ones are host. Suddenlink's using this CIDR notation for us. Right? So using the /24, the first 24 of these bits are going to be network bits. So let me go ahead and write that in. N. So that should be 8 N's, right? So these bits right here identify the network. So I'm writing 24 N's. And the way I know that the first 24 bits are N's is this number right here after the slash. All right, so I wrote 24 N's. What are the rest of the bits here? Those are called host bits. Host bits are property of the organization that has been given the network. These N bits belong to Suddenlink. I can't change them. But I can do anything I want with these last 8 bits. They've been given to me by Suddenlink. All right. So we have 24 network bits given to us with this address. And then Suddenlink said, hey, you can use these last 8 bits. I don't care what you do with them. All right. So what we want to do is, as a company, Joe Incorporated, that got this address from Suddenlink, is I want to break this range that they gave me into smaller networks. I don't want a network with 2 to the 8th computers on there. Okay? Remember, 2 to the 8th is 256. If I left this set up the way that Suddenlink gave it to me, I would have one network for my company, and I could put 256 computers on there. Well, I don't want to do that. I want to segment. I want to break up my big network into smaller networks. So I have 4 different areas in my network. I have an HR department. I have an engineering department. I have a research and development department. And then I have a operations department or a sales department. And I don't want the traffic from my research and development network or my HR traffic to travel over the network where the employees are, because I want there to be security on my network. Okay? And I want my network to be fast. I don't want broadcast messages from one computer to tie up the other 255 computers. So what I'm going to do is take this, and I'm going to switch some of these hosts into subnet bits. Okay? Now, remember, I can't change any of the network bits, only the host bits. These belong to me. So the first question I ask is, how many networks do I need? I said I had 4 different departments I wanted to reference, right? So I have 4 departments. I want to break this big network into 4 smaller networks. First thing I need to do is figure out how many bits I need to represent the number 4. So if I write the number 4 in binary, number 4 in binary is 4. Looks like that. Okay. So in order to be able to write the numbers 1 through 4, so 0, 0, 0, 0, 0, 1, 0, 1, 0. So that would be equivalent to 0. That would be equivalent to 1. This would be equivalent to 2. 0, 1, 1, which would be the number 3. In order to be able to count to 4, I need to use 3 bits. Okay. So the first thing I do is I figure out how many networks I need, and then I figure out how many bits I need to write the number 4. And it looks like I need 3 bits to write the number 4. So what I'm going to do is take these 4 host bits and switch them over to subnet bits. Actually, I need 3. So let me go ahead and erase one of those. I don't want to borrow too many. If I borrow too many, then I'm not going to have as many computers on the network. So I'll have smaller networks. So I want to fit it exactly the way I need it. Okay? So I said I need 3 bits to write up the number 4. So we're going to leave all the rest of these host bits. Okay? So we should have 5 left. Remember, I'm doing this to enforce security. So I'll have 4 different networks, and also to make my network smaller. So now I don't have 256 computers on each network now. I've modified the networks. So let's go ahead and clear this out. Now I only have 1, 2, 3, 4, 5. I've got 5 host bits. What number can I count up to with 5 bits? Think about that for a second. I can count up to 32 with 5 bits. So now, instead of having 256 computers on a network, I have 4 networks with 32 computers on each one of the networks. In order to figure out what the network numbers are for my new networks, I take the least significant subnet bit and figure out what that place value is. Okay. That place value right there is 32. Okay. So my new networks, my new 4 networks that I created are going to be 192, 128. My first network is going to be 0 because all of these subnet bits here are zeros. That's going to be the first one. My next number, my next subnet, I'm sorry, that should have been 64. Sorry, hang on. Let me fix it. Don't yell at me. Remember, we can't change any of the parts that Suddenlink gave us. So all our addresses are going to start with 64 because remember, we can't change those. Okay? Our next network is going to be in multiples of this place value right here. So we said that was 32. So our next network is going to be 32. Okay. The network after that. We just add 32 to it because that's the multiple. They call that the magic number. It's going to be 64. $192, 128, 64. 64 plus 32 is 96. That's going to be our fourth network. So these are the network ranges that we can use now. So what I can do is on my first network, I can use the numbers 1 through 31 or 1 through 30 for my computers. My next network range, I can use the numbers 33 to 62. So these are all of the IP addresses that are going to be usable for computers. 65 to 94. My hands get tired. And then 97 to 126. So what I've done is I've taken this big network that would originally have 256 computers on each network and broke it into four smaller ones that only have 32 computers on there. So I have smaller networks. The network is more secure. I have less broadcast traffic. I solve a bunch of my problems. There's actually more than just 4 networks. We can't borrow a half a bit with subnetting. So with these 4 subnet bits, we can actually also do 101, which is 5. 110, which is 6. And then we have 111, which is 7. So we've actually made 8 networks. We only needed 4, but we can't borrow a half a bit. So what we need to be able to do is use 3 bits for that. So we've actually got 8 networks. We've got more than what we need, but that's okay. We can use those networks later on. We don't need to waste them. All right? So we would just keep going on with this number, 192, to figure out the last 4 networks. All right? We don't lose those. We're not going to use them now. That's for expansion. If my company gets any bigger, I can have 4 more networks. I can just use them to make bigger networks later on. 96 plus 32 is 128. So you just keep figuring out those ranges. Once you get this magic number, this least significant subnet bit, then that's the multiple you're going to use to figure out your networks. Okay? This has been a quick overview of this process. Like I said, I don't expect you to be an expert in this, but I expect you to know why we do it and some general information of what we do to do it. Okay? You don't need to know too much about supernetting. Supernetting is the opposite of subnetting. Supernetting is taking smaller networks and making them into bigger networks. The reason we do that is to ease workload on routers. Okay? So it's called route aggregation or route summarization, and we take smaller networks, put them back as a bigger one, and it reduces the size of the routing tables, makes the routers run faster. You can do it. I don't see it done a lot, and I don't see, they probably do it maybe on the backbone of the internet. but you need to know what supernetting is. You don't necessarily need to know how to do it. Okay, it has been 2 45-minute periods now, so go ahead and take another 5-minute break. Okay? Take a 5-minute break, 10-minute break, 15-minute break, pause the video, and go take a break and let the stuff that I've talked about digest into your brain. The stuff we've covered so far is probably the hardest part. Now we're going to start talking about how to set up these addresses. So go ahead and take your break. Okay, you should be rested. Went to the bathroom, got a drink. We got probably about 20 more minutes to wrap up this chapter. The hard part is over. Okay. Remember, this is an overview of subnetting. This is by no means in depth. Later on, when you take the Cisco courses, you'll have to do some things that are a bit more complicated. Things like maybe subnetting a subnet. So you take a subnet and you subnet it to a smaller subnet. Some other things you'll have to do is subnet other classes of addresses, things of that nature. So remember, this is just like a little crash course on subnetting. I don't expect you to be an expert on it. All right, so here's a summary of these IP4 addresses. A host can be assigned only a Class A, Class B, or Class C address. Remember, we cannot use D or E. Every IP address configuration must have a subnet mask. You have to put a subnet mask with it so that it can figure out which network it's on. All hosts on the same physical network that's cabled together or on a wireless network must share the same network ID and their IP address. All host IDs on the same network must be unique. You can never have two IP addresses that are the same that are able to see one another. You can't assign an IP address in which all of the bits are 0. So you can't have a 0.0.0.0. You can't assign an IP address to a device where all of the bits are 1. So you can't assign an address of 255, 255, 255, 255. Computers assigned different network IDs can only communicate if you have a router in between them. Remember that the default gateway is assigned to a computer and must be the same as a network ID as that computer. So the gateway has to be on the same network. The address for the gateway has to be on the same network as the computer's IP address. You can assign multiple IP addresses to the same connection if you want. Sometimes they make things so that you might have like a web server and it has multiple websites running on the same computer. That's an example of when we would bind multiple IP addresses to the same network adapter. Here's an example. Notice for this particular example, if you look at the IP address and the subnet mask, these addresses are on two different networks. Okay? So this particular computer has a network interface card that he's got 2 of them, and they are connected to different networks. So this computer, this Windows computer with the advanced TCP/IP settings, could be acting as a router between 2 networks. So you can set up your Windows box to be a router. It's just a lot slower than actually using a physical router or hardware router. Okay? Notice they have a default gateway set. Okay. All right. All right. Remember, default gateways are optional. The other thing you might want to notice is that the default gateway isn't on either one of these networks that share these IP addresses. So this probably wouldn't work because the default gateway is not on one of the networks that the computer has an assigned address to. All right. So what we're going to do is the default gateway is always going to be the closest router interface. So wherever the router's IP address is, so the router's interface that is connected to this network where this computer is, the IP address is 172.19.46.250. That is going to be your default gateway. That's how you figure out what your default gateway is. So the IP and net mask we've already talked about. The gateway is always going to be the IP address of the router interface that's connected to the closest network. And the default gateway is going to be the way out of your network. So this is a network here. This is network number 2. This is network number 1. If I want to send a message from this network, 172.19.44 network, to the 172.19.46 network, okay, this is the network portion of the address, this is the host address, then I'm going to have to put a router in between there. This computer knows its address, its network address, so if it's sending a packet to the same network, it's just going to dump it out on the network to the switch. If it looks at the destination address for the packet and it doesn't match its network, it's going to send that packet to the default gateway instead of dumping it out on the network. So the computer is going to do a calculation for every packet it sends out, and if it's on a different network, it's going to say send it to the gateway instead of dumping it out on the network. And then the gateway, the router, is going to figure out how to get it to the next hop, the next spot. You can use a command inside Windows called route. That'll show you your routing table inside of your computer. So let's look at it on the next slide. So I type route.print from a command prompt. It's going to show me the routing table inside of my computer. So what it's going to do is process this routing table from top to bottom. Actually from bottom to top, and try to match the destination with one of these rules. Okay? So what it's going to do is it's going to look and see, is the destination network 172.31.255.250, does it match that network and net mask? If it does, then it's going to dump the packet out onto the same network. Let me make it green. Right? So anything where it says on link means that I'm not going to send it to the router. I'm just going to dump it right on onto the network. So all of these destinations, anything that goes to the 172.31 network, or the 172.31.210 network, or the 172.31.255 network, I'm going to dump it out onto the NIC and not send it to the gateway. Anything that has the 127 prefix, which is the loopback address, I'm also going to dump it out onto the link on the network. If my packet doesn't match any of these rules, it goes to this last rule here. The network destination is all zeros. That is when it doesn't match any other rules, it's going to forward it to the default gateway, which is that IP address there. So it's going to start at the bottom and go through all of these rules to see if the destination of the packet matches any of these rules. If it doesn't, this is a catch-all and it sends it to the gateway. And then the gateway is going to figure out how to route it to its destination. Some of the DOS commands we use to configure our Windows computer. Netshell is one of them. ipconfig. Ping. ARP. trace route, and NS lookup. And I believe we're going to go over each one of these tools, but these are the tools that are most commonly used to configure a Windows computer with IP. Net shell is if I'm using a Windows box that doesn't have a GUI or a click and icons and a mouse and stuff like that. So if I'm using a computer that just has a command line, I use net shell to do all my network functions. So I can set IP addresses. So this would be the command you would type at the command prompt to set the IP address for the Ethernet interface. Use this one to set a DNS server. Notice it's a very long command. You would have to type all of this stuff in just to set the IP address. It's a lot easier to do it through the point and click interface. But sometimes when you get to a Windows server, it might be running in core mode. Windows in core mode is not going to have a GUI. You would have to configure the server. You would have to type this entire command, and you'd have to have that memorized or have a reference book next to you. But we just know that net shell or net sh is a utility that we use to configure IP settings from the command line if we don't have a point and click environment. ipconfig is used in all configurations, whether it has a GUI or not, and I use it to examine the IP settings. ipconfig/all shows me all of the settings for IP for TCP/IP, the IP address and everything. Release says I don't need my address anymore, give it back. Renew says I need a new IP address. Display DNS shows me the DNS cache. You don't have to know what that is. Flush DNS will clear your cache. Register DNS will re-register your computer with Active Directory. So these are other tasks. Just type in ipconfig by itself will show you your IP address, but you can also use these slash options and it'll do other things also. You don't need to know these options. No ipconfig. Just know that one command. Ping command is to test connections between computers. So you type ping, and then you just type the IP address of the computer you want to try to contact. And you'll get a message like reply from, and then the IP address that you are pinging. If you try to ping a computer and it doesn't ping back, there's something wrong with your network configuration. So you shouldn't try to troubleshoot the browser and all the things at higher levels of the OSI model if ping doesn't work. So you should probably start at ping always to see if the internet's working at all before you start testing whether a certain website is working. Remember, the ARP command gives me the matches between IP addresses and MAC addresses. We need to know, if you look at a packet, you always have to have a destination IP address, and you always have to have a destination MAC address. So the ARP command gives us the information that we need to fill in all of the fields of the packet headers. Okay. Trace route tests the connectivity between two computers like ping, but it also gives you information about all of the devices in between you. So if you pass through 5 routers, when you're pinging the other computer, it'll show you what 5 routers you're going through. So it's going to show you information about the entire route that you take across the internet. NS lookup helps us to troubleshoot the DNS service. DNS service converts names into IP addresses. So if I go to, for example, www pitcc.edu, that is a DNS name. Using that, the computer cannot find the other computer on the internet. What has to happen is DNS has to convert that from the name to a real IP address. So every time you type in a website, the computer does this translation from this name into an IP address. And then the computer contacts the IP address, not the name. Okay. The reason we have this service is because it's really hard for us to remember these numbers. You wouldn't know to go to 160, 170, 180, 190 to get to Pitt's website. But you do know that you type www.pittcc.edu to get to the website. So DNS does that translation for us so that we have memorable words that we can use to find IP addresses. Right? We test the DNS system by using NSLOOKUP. So all of these command line tools are used to troubleshoot your internet connection. So we said there was internet version, IP version 4.1, 4.2. We went through all the revisions. We did subnetting. Problem is, even with subnetting, we still ran out of addresses. So somebody said, hey, wouldn't it be nice if we could use our private addresses from the ranges we came up with? That's the 10 network. Wouldn't it be nice if we can use these ranges on the internet? Or not use them directly on the internet, but give those people with those private addresses some kind of access to the internet. Okay. So we might have 256 computers on our network with these private addresses, but usually only 10 of them are connected to the internet at the same time. NAT gives us a mechanism so that we can share IP addresses. So we have 256 computers, but we have 10 IP addresses that's given to us by Suddenlink. NAT allows us to take these private ranges, and when it gets to a router, swap out the IP address of the private range with a public IP, so that these computers can now use the internet. Even though they have repeatable IP addresses, when it gets to the router, it lops off the private address and then gives it an address that could be used out on the internet. And then the router's going to remember who sent that packet so that you can communicate. So let's see. Right? So here we go. So we have a computer that has one of these private ranges. Normally, these computers would not be able to use the internet. But I have a special feature on my router called Network Address Translation, where when a packet comes from this computer and hits the router, normally it would drop it. Since it's running Network Address Translation, it's going to look in its pocket for an address that it can be used out on the internet. What it's going to do is it's going to take that address off, that private one, and put on a public address for that packet, so that it can communicate on the internet. When the packet comes back from the internet, it's going to lop off that public address and put the private address back on there. So it's going to give it back the 10 address, and it's going to go back to the computer. So the router is going to work in place to be like a man in the middle between this private address and the internet, and fix up that IP address so that you can get out on the internet. So that would be what? IP version 4.3, which is NAT. So now we can use all these private addresses and still have access to the internet. So this NAT stuff really, really worked well. So well that people are resistant to move into IP version 6 now, because we have plenty of addresses now. If everybody can use all of these private addresses inside of their company and still be able to get out to the internet, then there's really no reason to move to 6. So they kind of shot themselves in the foot by making this work so well, because now we have trouble with pushing people to version 6, which is a lot better than version 4. We can also do port address translation. Port address translation allows me to use one IP address. So this is what your router at home does. Okay? So you're connected to Suddenlink. For a residential customer, you're only going to get one IP address, right? If I'm a big customer company, they might give me 10 IP addresses. Since you're at home, Suddenlink is only going to give you one address, which is 198.168.123.100. Your router is going to use something called port address translation, and it's going to take all of these packets from these private addresses, and not only is it going to change the IP address, it's also going to change the port. Okay? So that all of these computers with different IP addresses can use the same IP address on the outside. It just randomizes the ports that you're connecting from. So that's called a port address translation. Whereas NAT, you have a one-to-one. You have a private and then a public. PAT is I have a many-to-one. So I have many IP addresses on the inside using one IP address on the outside. So that's the last Band-Aid or patch they put on IP version 4. And like I said, it's worked really well. Like I said, you use it on your router at home. Because probably I've been talking about this IP stuff, and you've noticed maybe your computer has a 192.168 address. And you said, well, I thought Joe said that, if you had 192.168 address, you couldn't use the internet at all. Well, until they put this Band-Aid on the IP version 4, network address translation, a port address translation, you couldn't use the internet, but now you can. Remember, IP version 4 was developed in the 60s, so it's going on, 60 years now? And its address space is being used up. Right? They came out with a new standard. It took them about 10 years. It's called IP version 6. IP version 6 addresses look very different from 4 addresses. Okay. Here are the features of IP version 6 over 4. Larger address space. So now, instead of having 6 billion addresses, I think 6.2 billion addresses, we have 2 times, no, hang on. Oh man, I wrote it wrong. Let's see. I think it's 2. I can't remember now. It's going to be 2 to the 128th power. Whereas before we had 2 to the 32nd power, it's going to be I think it's 32 undecillion addresses. Undecillion. So it's a lot more addresses. All right. The address space is in a hierarchy. And what that means is I can look at an address and tell which country the computer's in. I can tell what company owns it. So I have location built into the address now, so that I can find out where a computer is. All right. The computer can configure itself. I don't have to walk around and put IP addresses in anymore, right? Like version 4. We have quality of service support, QoS. That means that I can prioritize video and voice over email. Security is built in, whereas no security was built into version 4. Support for mobility, so I can move from network to network and not have to change IP addresses. And extensibility, which means I can add features to it. IP version 4 was created in 1994. We don't do subnetting like we did in version 4 anymore. The IP version 6 address is hexadecimal. So we're moving from using decimal to represent the number to hexadecimal. Hexadecimal numbers are 16-bit numbers. This is what an IP version 6 address looks like. Notice it has letters as well as numbers in it. The first part of the IP version, the IP address, the first 48 bits. I'm sorry, the interface ID. So this is going to be the last 64 bits of the address. First 64 bits are going to be used for the identifying the ISP and the geographic region of the address. The last part, the last 64 bits, are going to be built using the MAC address of the computer. Okay. So then we have 64 minus 48. That's going to be like 14, something. No. So 58, 7, like 16 bits left. The last 16 bits are going to be used for a value FFFE, and so it's just going to fill it in with zeros and ones, a prefix. So the last part of your address that we typically use with version 4 as a host address is going to be built from using your MAC address, so that we don't have two computers with the same IP version 6 address. It builds it from your MAC address. Okay. So the structure of IP version 6 address is different. Right? So the first half of it is going to tell us what part of the world it's from. 2, 3, 4. And then the last part is going to be made out of the computer's MAC address. Let's see what else we need to know. There's 3 different types of addresses: unicast, multicast, and anycast. Notice we're missing broadcast. We don't have broadcast in version 6. A unicast address is given to a computer, and it can communicate with one computer at a time, a one-to-one communication. That's typically the address you're going to use. A multicast address is for sending messages to groups of computers. An example of a multicast function would be if I'm sending video to a group of users. I don't have to send the video to all of the users on a network. That would tie up my lines. I can use multicast to send video to select computers on the network. Anycast addresses sends the message to a group of computers, but only the closest computer gets it. So it's used with like data centers where, you're trying to access files in the cloud, but you only want to get the files from the closest data center. You don't want to go all the way to Japan to get a file that's available in Virginia. So Anycast will send out a request to the cloud, and only the data center in Virginia will respond to the message. The data center in Japan will get the message, but it knows that the Virginia data center is closer. So that's what Anycast is. There's 3 different types of unicast addresses. So drill down into unicast. Link local addresses are analogous or the same as the AP/IPA addresses. It builds that address. That address is used only on the local link or only on the local network. Okay? It can't. The router drops it. So any address that starts with FE80 is not routed. So a message that's sent to FE80 is not going to be forwarded by the router. Unique local addresses are analogous to the private addresses that we used in version 4. We can repeat them. We just can't repeat them on the internet where another computer will see the same address. Okay. So addresses starting with FC or FD are going to be unique local addresses. It can be routed within your company, but once it gets to an edge router that connects to the internet, those packets are going to be dropped. Global unicast addresses are addresses we can use to access the internet. They can be routed. So we're identifying these different types of addresses by scope. And by scope, I mean how far is the packet going to go? These stay on the side of the router interface with you. So they don't cross routers at all. These can cross routers, but only routers that are owned by the same company. These can cross any router and can get out to the internet. We have special addresses. If you ever see a ::1, that is a loopback address. So if I ping or use a utility to contact ::1, that's the computer I'm sitting at. Sometimes we use the 0 address as a placeholder. When we have a 00 address, all zeros, we do a : dot colon. 2001 DB8 is going to be documentation. What that means is reserved for examples in books. So if I'm doing a lab in my book, they might use that address, and that guarantees it won't conflict with other devices on the internet or on the network. You can still subnet in version 6. It's going to be completely different than 4. We're going to have that prefix. Most of the time you're not going to have to because we have so many addresses. Most of the addresses that you get are going to have a /48 prefix. You can subnet with version 6, but like I said, most of the time you're not. So out of the 128 bits, the 48 are going to be fixed. Okay. So you're not going to change those. That's what you're going to be given. The next 16 bits on your network that you're given can be used to subnet if you want. And then the last 64 bits are going to be used for host IDs. Okay, host bits. So we still have that concept of network bits, subnet bits, and host bits. Remember, a multicast address is used to send messages to groups of computers. Anycast addresses can be assigned to multiple interfaces. They're assigned on routers and are used to allow other IP version 6 computers to deliver packets to the nearest router on a subnet. So it's only going to be delivered to the nearest device that's part of that Anycast address. Remember that we don't need to configure IP version 6 with an address. It can configure itself. It uses its MAC address to figure out its host ID, and it uses messages from a router to figure out what network it's on. So that's called stateless auto configuration. It lists for something called a router advertisement or an RA message. The RA message will give the computer or the host the network portion of its address, and then the computer will build its own address using its MAC address for the rest of the address. Stateful auto configuration is something else where I can actually send it other information than its IP address. Okay. So it uses the same kind of auto configuration that stateless uses, but I can also pass it information like DNS servers and other information that I need to use to configure the computer. Okay. All right. So to wrap up this chapter, there's a couple of things that we can use to transition from 4 to 6. You can have 4 to 6 on the same network. Most Windows computers run both addressing at the same time. So your computer's going to have a 4 address and your computer's going to have a 6 address. Okay. We can also do something called tunneling. And what we'll do is we'll have older equipment running IP version 4, and we will shoehorn IP version 6 traffic and put it into packages that travel over IP version 4 network. So that's called IP 6 over 4 or 6 over 4. So all of the routers and all the devices in between understand 4. I'm going to take 6 and place it in a 4 packet, and that's called tunneling. Intra-site automatic tunnel addressing protocol is something that is a Microsoft protocol and is used for that resolution of the IP version 6. Okay. Then we have another protocol called 6 to 4. And then the last is called Teredo. Okay. If you have NAT running on your network, then NAT usually will break these 3 technologies. Okay. Because NAT is running, it tampers with the header on the IP packet. And on version 6, if you tamper with the header on the packet, it throws it away. It figures it's been hacked. So Teredo allows us to use 6 over a network that's using NAT. Okay. So tunneling is a network protocol that allows transmitting a packet in a format that's otherwise incompatible with the network. Right? So this is IP version 6 over 4. So it takes an IP version 6 packet, IPv6. It runs it through the OSI stack again, and then wraps that version 6 packet inside of a version 4 packet. So as you can imagine, you take a performance hit because you're wrapping the packet twice. Once the packet gets to the other end, the other router strips off the 4 headers and then dumps the IP version 6 packet out on the destination network. All right. Like I said, once it connects to the other router, it dumps it out with this address. It drops the IP version 4 address. ISA-TAP is used to transmit IP version 6 packets between the dual layer host. So when you're running 4 and 6 on a Windows machine, you can route version 6 traffic between 2 computers over the 4 network. But you'll only see that on Microsoft boxes. two Microsoft boxes talking to one another. 6-to-4 tunneling provides automatic tunneling of version 4 over an IP version 4 network. So what they do with that is they take and they put this prefix in front of the version 6 packet, and then what it does is I think it uses your IP address as the rest of this address here. Yep. You have to have a public address in the second part of the version 6 address. So you put your version 4 address and you tag it on behind 2002. Okay. Remember, you can't use private addresses in 6-to-4, which really limits its use. Teredo is an automatic tunneling protocol. Solves the problem of 6-to-4's requirement of a public 4 IP address and its inability to transfer NAT. So if you use a network address translation at all on your network, you need to set up Teredo. Teredo's nice, but it takes some setup, right? You need to have Teredo servers and stuff, things of that nature. Yep. We will go over IP version 4 more in Net 125, and you'll also go more in depth into version 6 in the next classes that you're taking. Right. So we're just over 2 hours and 20 minutes. So like I said, this has been a long chapter. You can rewatch it over and over. It's going to be on YouTube, and like I said, break it into sessions so that you can absorb the information that is in this lecture. I hope it helped you out a lot with this chapter. Like I said, this chapter is very technical, and I hope that you're going to do well in this class and you continue to watch the lecture videos.